Hello, everyone. We'll kind of let people start to get into the webinar. But yeah, thank you for attending today. I'm excited to talk a little bit more about some of our isochrone technology and some of the new pieces that we brought into Wherebots to create isochrones in a distributed manner. So we'll kind of get into that, what the problem is around that, why it's particularly difficult, especially doing that at scale. And then we'll show some functions on how you can generate your own isochrones and do that within the Wherobots platform and show you those pieces. And then on top of that, actually demonstrate some different functionality, but pretty common analysis, which is figuring out population within a specific area, drive time area with those isochrones. So that's the plan for today. And wait a few minutes for people to join into the webinar. So we'll let that happen. But in the meantime, if you don't mind, I always kind of like to know where people are joining in from. So if you want to just drop in the chat, share where you're calling in from or joining in or zooming in, whatever the verbiage you want to use is, and let me know. And then also kind of what brought you here today, why you're interested in isochrones or Apache Sedona or Wherobots or anything like that. So yeah, feel free to drop that in the chat, and we'll give it like a minute or two here, and then we'll go ahead and get started for today. And then any questions you have, you should have access to like a little Q&A section down below. So go ahead and use that. You can drop any questions in, and I can start to answer those as we go along. All right. Think we can probably get started. No one want to share information, which is fine. So that's all good. But if you want to just drop that in chat, and any questions you have, we can get started there. So the first, I kind of want to start to frame a little bit about isochrones generally and why they're particularly difficult to create at scale. And then kind of talk about some of the existing solutions that exist out there for creating isochrones as they exist today. And then we can kind of dive into the demo. We'll talk a little bit about just a few different content pieces I'll point you to. We have like a blog announcement and some other things as well that I think are worth reading. So I'll make sure to share those resources if you haven't seen them yet. And then we'll get into the actual kind of demo of building all this out. So if you're not familiar with isochrones. An isochrone is kind of a fancy term for a drive time radius. So in a normal radius, it's just a circle around a point or location that could say how, what's the radius or distance around this for 3 miles. And you create basically a circular buffer around a point, and that polygon represents everything that falls within 3 miles of that point. Now, of course, in the real world, we usually use roads to get places, not just kind of walking in, in whatever direction we want. So eventually you have to account for travel time by road. And that's usually measured in distance or in time, right? So there's a concept of like a iso distance, which is basically how far could I get in 3 miles on the road network, which is not a dissimilar problem. But oftentimes people measure that by time, right? And that's usually the way that you estimate that, because 3 miles in one direction might not equate to the same time it takes to get 3 miles in another direction. So it is a valid, like an iso distance is valid, but usually isochrones is how we measure that. And that's usually by a concept of, it'll take 5 minutes to get here or something like that. And you want to measure that to say, from this point, how far can I get in any direction using the existing road network in 5 minutes, right? And that can, there's a few different intricacies with how you measure isochrones. One of which is, where does the road network have intersections, and how long do the intersections take to change over? Is there traffic or is there not traffic, and things like that. So you can kind of start to, you know, understand all the pieces that go into this puzzle. But basically, what you have to do is, from a source point, you have to figure out, okay, along every possible route that you could go, how far you can get along the network, and then create a polygon. And you can create very accurate travel time isochrones, like highly accurate, or you can create them in a more generalized way, which I think is probably, generally for an analytics use case, a little bit better to go, because there's so many different factors, like I said, that can go into deriving a drive time isochrone. But they're used in so many different fields to measure things around service or access, right? I should also point out that you can create isochrones for many different travel types. You could create an isochrone for cycling and using streets and safe cycling. You can create an isochrone for walking, and you can create an isochrone for transit distances as well, using the transit network. So you can build all those different things. And it just depends on kind of like the services underneath it. But I think most generally, at least, in the United States and other countries that, depend on car networks, car is generally the way that's measured. So what does that mean for actual, application of these things? Number one is that drive times can be used in a lot of different industries. You could measure drive times to a specific retail location, restaurant, store, gas station, anything like that. You can measure that. And it's usually used to understand, market dynamics around, cannibalization, or, potential profit, how many people can get to that area, what's within the distance, competitors, all those different things. So like retail is usually the top of mind one when it comes to this. But anything from urban planning, if you want to look at access and to different locations and things like that, healthcare, how many people can access these types of doctors within these distances. And then you start to bubble that up to analytics use cases, right? So how can you look at that and aggregate those measures across demographics, how many people are in that area, or how many, points of interest or transportation stops, or what are the, the nearest, seven things, like, could be, grocery stores or anything like that, right? Anything with a physical location is kind of can use and could probably drive value from isochrones. So you can do quite a bit with these. Now, that said, there's two challenges that are unique to isochrones that, especially when doing them at scale. Now, doing them one-to-one, there's services that can do that. You could build your own service. So you can use things like the open source routing machine, or OSRM, that can create routes, and then you can create a polygon around that. I've used PostGIS with PG routing in the past. That's another open source option. I think there are some open source like isochrone providers, but most commonly that's done through APIs, specifically with large mapping services, things like, Google Maps, Mapbox, Here Maps, and then many other smaller providers. There's quite a few of them, and they provide these via API. And usually, an API is serving a one-to-one. You're requesting a single location, you get a single polygon back. They generally do have batching of these, but it's not in any large number, 5 to 100 or something like that. So there's, you could batch chunks of these over time, right? And of course, you're paying by the request, right? Every single time you're paying by the request. So that's a big problem if you have to account for cost and you're doing these for hundreds or, thousands or millions of locations, right? It can get quite computationally expensive. So that is kind of one component of it, is the computation component, and the cost component. I should bundle that and say that was point one. Point two is that the things you want to measure intersecting those polygons, doing those types of joins at scale can also get computationally complex. Now, point and polygon um, is kind of solved. How many points are within this? I mean, there's lots of ways to do that, and lots of even query engines like your data warehouses and things like that can do this quite efficiently. Big, your data warehouses like Snowflake or BigQuery and even PostGIS, and you could even do this in Python if you wanted to that way. So that's something. But when you have to start doing more complex joins, things like overlapping census demographics, which is known as area weighted interpolation, that's when you have to consider some extra options and extra computational power. So the key there is that, let's say I want to count how many people live within a specific isochrone, and I'll illustrate this on the screen in a minute. But let's imagine that you have a drive time isochrone that kind of look like these kind of funny blobs in a way. And you say that, I want to, first of all, I want to figure out how many census boundaries intersect that boundary. And that's an easy problem to solve. It's a simple, spatial intersection. But then you have these census boundaries that might be like half inside, half outside. And that within that, you can't know within that census boundary where more or less people live. You could try to derive that, and it is there are procedures to do that. But for now, let's not assume that. Let's assume that we just want to count half of that population, the amount that overlaps. That's what we want to count as inside. So we have to basically do a clipping of that polygon, and then count the proportion of that. So if it's 50%, we count 50% of the value and put that in there. And that requires some extra spatial functionality, which most of these query engines have as well. But computationally, it's a very cost heavy operation. And that's what I'll show today. I actually put together a guide on this, and kind of, comparing it to BigQuery, which in this case, Wherobots outperformed. I think what's more interesting is how we did it and using kind of the open core tools. So I'll reference that as a follow-up here so you can take a look at that. It was a guide on LinkedIn that I published about this, and I'm working on a blog post about it as well. But that's where you start to do and get into these computationally expensive things. On top of that, you might want to add not just population, but percentage or income or all these other factors that factor into what's going into that area you want to do. And that's where, having a data processing pipeline that can both efficiently produce the isochrones and then also allow you to do the spatial analysis in the back end can be really efficient. And that's what Wherobots really solves, is doing those two pieces together. So I saw one comment from Tim, which I'm going to read here. So they're currently using radius and bounding box for like linear distance, which for their tool kind of results in some difficulty in recommendations. So it's computationally expensive and financially expensive, which is what we're describing. So looking for different alternatives to that. So hopefully we'll showcase what we can do there with that and go from there. So I'll share my screen once again. Any comments or questions, drop those. I'll be poking back and forth between the Zoom and the demo here in a minute, and we'll go from there. So first off, I wanted to point out the blog post. So one thing that comes with our pro plans, if you choose to sign up for those, is that you actually get access to a data set where we created isochrones, pre-computed them for the Overture Maps dataset, which is 13 million places in the US. So we have that as a data set you can just sign up and start to use. But more importantly, it's pre-computed isochrones. And you can basically, the way we did that is with these two functions we added. So we added one for a single isochrone and one for multiple. When I mean multiple, that could be like, I need to calculate 10, 15, and 20 minutes. And we did that there. Those all come along with the other functions that we have. But this is what it looks like. It's nothing too crazy here in terms of the SQL, just ST isochrone. You provided a geometry, a drive time. Car is the only option right now, but we're adding more. And then the last function here, that false argument, is if you want it to be inbound or like reverse, how many people can reach that location coming towards it versus going away from it. And I actually think that's a unique thing that we have, is to say that, okay, instead of it just from this location leaving, how many can come into that. So, so that's what we did. We built this data set here so you can actually see these data sets. And then this is what a sample travel isochrone would look like. Now, other services provide them with like a certain higher level of granularity. This provides it with a little bit more generalization, which is actually, I think, in good in this case, because traffic, as you know, changes throughout the day, right? It's hard to say at that precise time or conditions if it's truly at a 20-minute distance or a 15-minute distance or anything like that. And for analytics, you want some generalization there, primarily because you know anything can affect traffic. If there's a road closure, if there's weather, if there's traffic, any number of factors can affect that. But this gives you that general, this is about 20 minutes from this place. So that's what we did. There's a blog post that actually talks about doing some site selection for fire stations here. We use that on top of STDB scan and then figured out where there's gaps within that. So these are places that have high risk outside of 30-minute reach across the United States from a fire department. So you can see where there's these gaps in this. And then there's probably areas here that have lower population as well. But that's a simple kind of view of what that would look like. So this is the data set I'll be using today. There's 5, 10, 15, and 20-minute isochrones, and that was generated using the isochrones function. It's for all 50 states and territories. It's about 13 million different places, and we generated 52 million isochrones, right? So that's how we're able to do that. So you can actually get access and use this data set today. It's pre-processed, so there's nothing you have to do in case you want to use those functions. So there's all of that that's kind of ready to grow. So that's the detail on the data set. The detail on the functions is here. And all you have to do is basically create a data frame or a table in WherbotsDB, which is Apache Iceberg on the back end. And then you can compute these and spit them out in any format you want. You can save them as files for GeoJSON or CSV or GeoParquet or even shapefile or anything like that. So you can turn the files out in any format you want, and then effectively you can kind of create a pretty efficient data pipeline through that. So that's what you can do. And like I said, there's two different functions here. There's the ST isochrone, which is a single geometry. So you provide the geometry, the time limit, the mobility type, and if it's inbound or not. And then IST isochrones takes in an array of more than one to calculate that. And then you actually have access to all of these different functions here that you can mix and match data with, which is what we'll show in a minute. So to do that, I started my notebook here, and I'm just creating a isochrone of 2 minutes. So if you see, I'm just going to create a single geometry here around a point. This is I believe it's called the crypto.com arena in downtown Los Angeles. It's where the LA Lakers and I think the LA Kings and I believe the Sparks. I believe that's all the teams that play there. Now they have a different different arena for the Clippers. So, but it's formerly called the Staples Center. That's the way I remember it from growing up. That's the arena in Los Angeles. So that is right about here. If you can see the Staples Center, as it's called out here. And I basically am creating an isochrone around that point for 2 minutes by car, and it's outbound, which is what the false argument passes here. So I can run that, and then to create the map, just to visualize it, I can do that here. So that's going to create the isochrone on the fly, and this is sort of what it looks like. Now, this is kind of assuming the most perfect ideal traffic conditions, right? So that this is where I could reach in 2 minutes if everything was there. But if it's busy after a game, I might want to weight this and say it's probably about it's probably way worse. So I can just add a simple multiple here. You can change that number and adjust it and play with that if you want. We don't bring in live traffic as a calculation. So this is what that would be for like if traffic was really bad. So you can see here, you can't really get too far. And it starts to look a little bit more accurate as it gives you the specific streets. But as it gets out farther, it gets a little bit more general as you get access to highways and things like that, which is to be anticipated. So that's what that looks like. We can also, let's maybe just do a 1 minute here. We can also set this for true, and this will show us all the places that can be reached coming towards the arena. So these are all the places that if you were going towards it and you started at that edge of the polygon, you could get to the arena. And so this is what it looks like for inbound. And then this is what it looks like for outbound. Change it back. You can kind of see that here. So this is that single function. You see it looks slightly different here. Not exactly, the same, but pretty close. So that's the function. And then if you want to create multiple, you could use the function isochrones, just adding an s on the end. And you would change this to an array and give it the numbers that you wanted, 1, 2, 3, like that. And this will work. I can run this here. And then, oops, let's see, did something wrong here. isochrones. And we can isolate the contours. We'll add another there. And then I can just show you what that looks like for that. And I will basically be getting an array of geometries here. So multiple geometries that I can get back. So you see there, that's what I get there. Or sorry, that's a single one. If I want to pass false, I can get an array of geometries here. So you can do this and you can do it over any scale of data that you want, right? You can use this across a table of points that you have. This is just showing that single point just to illustrate it. You could do it with as much data as you want. And then you basically use the appropriate size compute instance in Wherobots to size that up correctly. And then that will all store as this is currently storing as data frame, and then you write that to a table using some of the writing functionality within Wherobots, which I'll show in a minute. So that's that. There is no limit on this. Like there's no per call request. You basically pay for the processing time and the processing size that you use. So if you're running a medium runtime or a large or a small, that's basically billed at a number of spatial units per hour. And if you're using it for a minute, you get billed for that minute. If you're using it for 10 minutes, you get billed for those 10 minutes. And that's pretty much it. You don't get billed for anything less or more. And then once you have created the isochrones, they're yours when they've been written to table to use as however you want, right? So you can use them in whatever way you see fit. So it's not like you have to regenerate them on a specific interval. Some providers have that requirement where you actually have to update it because they've added refresh data. You just get to use them at scale. But I think what's probably potentially even more interesting is the ability to intersect that with other data. So this is what I'm doing here. And I'll just show you and illustrate also the ability and speed to do this. So what's happening is that I am having a query here with two parts. So this first part is I have a table of census tracks, which is stored in WherbotsDB now, and that's stored in Apache Iceberg. And if you're not familiar with that, it's basically a table format that sits on top of Parquet files that allows me to store data as, just GeoParquet. Once I write it into the catalog, it has the schema, the history, everything like that is written into it. So I can do all those different, kind of calculations super efficiently. And I can even write this into a data pipeline if I wanted to say, okay, well, I get a new batch of geometries in, just insert the new ones and find those and then add the isochrone on, so I don't have to like recompute everything. I can just add those and efficiently add those into the table, and then I have that complete historical view of the data and I'm ready to go. So that's the advantage of Iceberg. It also has built-in partitioning. I said the schema evolution. You can change schemas over time. All of this stuff is really kind of built in for you to use. So, and it has all that history behind it as well. So if you're doing like this on a frequent basis, adding new locations, updates, it's really built for that type of process. So what I'm doing here is basically taking the ID of each isochrone from that pre-computed Isochrones dataset. I'm doing a small repartition here, which basically means I'm spreading the data out evenly over the compute nodes. It's just kind of a process that helps that run more efficiently. If you're using something like a data warehouse to do this, like BigQuery or Snowflake, it kind of does some of that behind the scenes for you. But you're of course locked into their internal storage system. It can be a little bit more expensive. And then the compute, it kind of doesn't allow you to scale and control that. Here you use and scale the compute not based on query, but based on the time it is active. And you get to have full control over that, as well as the partitioning and things like that. So we actually put more of that back in the user's hands, which is a big advantage. Now, to calculate the overlapping area, that's this section of code here. So let me try and zoom in all the way so it's easy to see. So I have this field called total population, or total pop. That's just one metric. I could calculate as many as I wanted to from here. But what I want to do is imagine that in this isochrone, there's a box over this split into 4 parts. For each of those 4 parts, I want to figure out what percentage is overlapping the isochrone, take that number or that decimal and multiply that by the total population in that area. So if each square has 100 people and this one overlaps by 50%, I'll count 50 people. This one overlaps by 70%, I'll count 70, 30, 30, and let's, for argument's sake, say 80 here. So that's what that would do. And I'm just doing that at scale. It could be as many polygons as was required, but it's going to capture all those edge cases within that. So then what I'll do here is basically say, take the total population and multiply it by this fraction. To get that, I'd get the area of the intersection, right? So ST area, and then the intersection here, which is the intersection of the geometry of the census polygon and the geometry of the isochrone, and then the shape of that area, which is the census polygon, and then divide that by the total of the census polygon. So out of that, what part intersects is just simple arithmetic here. And then I'm going to multiply that by here. So if this value, everything in here equals 0.5, and this is 100, the return value would be 50, if that makes sense. And then all I'm doing here is I'm passing that to say where those things intersect. I don't care about anything else that doesn't intersect that. So that's just adding that spatial predicate that allows me to run that more efficiently. And then once I do that, I join that back to the isochrones table with the geometry in it. So that makes that a little bit more efficient. So for this one, it's doing that for every one of those isochrones in the state of Texas, which is about 1.3 million to calculate that. So we'll run this here. And then just to show you kind of some of the speed here, this is going to run. It takes anywhere from like 50 seconds to a minute and change. Some of that's just depending on the internet bandwidth to communicate the data back. So there's like extra time tagged onto this in terms of the internet communication back and forth. But as you can see here, it's going to work over those 200 partitions. It's going to run through this pretty quickly here. And then that will create that and store that as a data frame. So once that's ready to go, we'll take a look at the data and then go from there. So I just want to check, see if there's been any other questions that have popped up. Let me see here. All right, looking good so far. All right, so let this finish up, and then what I'll do is I'll kind of show you how to write this back out to storage so you can write in any format that you want. So that's done, and you can see here for this drive time, there's only 508 people in that area. This one, there's 253,000. So it varies depending on where these are. Of course, this one's in a denser population area. This one's in a very rural area. So that's in those different areas. And look, it took exactly a minute here. So that's about what we expect, which is great. So then to write that data out, all I have to do is call this function here. We're using our internal cloud storage. It's a cloud storage component that ships with our product. So you get access to a private S3 bucket, but you can connect your own and store your data and your Iceberg catalogs there. And you can actually write this to an Iceberg table and query that in anything else you want. And Iceberg can get queried in BigQuery and Snowflake and DuckDB and Trino and another instance of Sedona. Like there's all these different ways to actually access an Iceberg query, which is very efficient. So you can use us literally just for this one operation and then take that out to whatever existing engine that you have and use that there. Or I think there's also PyIceberg as well. I didn't mention that one, but basically that's where you can do it. Or if you want to write it to files, you can write this as GeoParquet. You can write this as CSV. You can write this as GeoJSON, whatever you want. You can actually write the file out to do that. And that will write and save that as you can either have it as a single file or as a partition file, should you choose to do that. But that's basically it, right? What's so cool about this, and to kind of connect this to the bigger whereabouts picture, is now you have this ability to create these very detailed data points about different locations and what's inside of them. You can use census data. You could even use, k nearest neighbor functionality, which we have. You could intersect this with, 30 different data points from this data set if you wanted to. You could do raster components with this as well. In the last webinar, I did a demo with that where we found the most, frequent, or the mode land cover type within these different isochrones. You could figure out elevation, you could figure out crops, you could figure out all these things that exist inside of this. And it gives you really rich spatial features for an application-based use case where you want to cache these drive times and have people query it and have much, faster response time. You could have it for machine learning use cases to take upstream. You could take it for and plug this into an LLM. How many people live within a mile of this location, and now you have this data. So you can do this at scale, and it solves really those two problems that I talked about at the beginning. Number one is the scale. Like, I just did this for 1.3 million locations in a minute, which is quite scalable, and I'd be hard pressed to see other solutions do that. And then the other piece is the complicated spatial join. Like, this was a single join here to do that overlap, but you could do that across multiple different measurements and things like that. And you can completely build that into a data pipeline, do the upserts, inserts, updates, and everything here is just cloud storage. And when I'm done with this, if I want to do this in a notebook, all I have to do is just shut down my compute here, just hit destroy and I'm done. Or if you're doing this with our Airflow service, it will shut down automatically and only consume that compute that it requires for the runtime, which is super efficient for you as the user. So to use this data set, if you actually want to use this data set and use these functions, that is part of the pro plan. To do that, you can go to wherebots.com, hit try, and then go to the AWS marketplace here. And that will allow you to actually sign up and use Wherobots through your AWS account. If you have existing AWS credits, it uses it right there. Nothing else that you need to do, and then you're ready to go. You just connect your S3 storage and you're off to the races. So that's kind of it for today. I kind of packed a lot in the 30 minutes. So I wanted to just check if there are any other questions from the group, anything that wasn't clear, anything about maybe a use case that you have to see if that would work with this functionality, and anything else I can help answer for you about whereabouts outside of just the stuff we talked about today. So I'll give, if you want to take a minute to type those, I'll take a look and go from there. As a last housekeeping point for today, we'll be sending out the recording of this afterwards. So if there was something you didn't catch, we'll send this out as a recording as well. So you'll get access to that. And then we'll send out some of these resources as well with the blog post, the actual functions to run this. And then I'm going to prep this in a notebook that people can use as well. So if you want to try this out, you can do that there too. But go ahead and get signed up if you want to use the Isochrone functionality for a pro account, or if you want to just try this out on your own with just general functionality, you can sign up for our community edition as well. So I'll wait 1 or 2 more minutes if there's any other questions, and we'll go from there. I'm not seeing any specific questions unless someone's typing a very long question, which has happened before. So I'll start to wrap it up, and if I see a question pop in, I will answer that at the end here. But once again, thank you all for taking the time to attend today. If you do have questions that after this, you can feel free to reach out to me directly. My email is just matt@wherobots.com. So you can shoot me an email, or if you want to chat on LinkedIn as well, you can find me there. And yeah, thanks for taking the time to check this out. I hope this made sense and is valuable for some of the work that you're doing. And yeah, I hope to see you in the platform as well. But with that, I'll wrap it up for today. Thank you all for attending. And yeah, hope to talk to you all soon. Take care.